Hello, good morning class. Today I will be discussing to you about the DC biasing of a bipolar junction transistor. So in a bipolar junction transistor or BJT, as you can see here in the graph, this is the operating uh, points of the transistor. So we have this what we call the quiescent point. So these are the points as you can see here, designated as A, B, C, and D. So these are called as Q point, quiescent point, wherein quiescent means silent or quiet. So these are the portion wherein this is the portion wherein the transistor is in operating mode. Okay. Then you also have this operations that you need to understand about the linear region operation. So when we say linear region operation, it is where the base emitter junction is being forward biased. The base collector junction is reverse biased. And cutoff region operation is where both of the base emitter and the base collector junctions are being reverse biased. And the third one is the what we call the saturation region operation, wherein the base emitter junction is being forward biased and the base collector junction is also forward biased. Next. So first we have this fixed bias configuration. So it is called fixed bias because even though the network employs an NPN transistor, just like in our example here, wherein we are given a schematic diagram of a NPN circuit, a, the equations and calculations apply equally to a PNP transistor configuration. So no matter whether it is a PNP or NPN, we apply the same equations and calculations. But what is the difference is that we merely change all current directions and voltage polarities. Okay, so this is a fixed bias circuit, and the DC equivalent of this one is this circuit diagram beside it. So as you can see, so this one can also be interpreted as this, and as you have noticed, what happened to our capacitors? So these capacitors becomes an open circuit. Okay, so this diagram is just like this one. Right, and we have the forward bias of base emitter. So as you can see here, so we focus at this side, the base. So this is the base of the transistor, right? This is the base and this is the emitter. So being the base emitter being forward biased. So the equivalent circuit of this is the loop. The loop that we will be tackling will be from the VCC. Okay, VCC the up to the resistor B, and then the RB, and then going down to the base, then to the emitter. So that will be the flow of the current IB. Okay. And then getting the equation, we have VCC. This one, VCC, so positive going outside the positive, minus IBRB minus VBE. This one here equals to 0. Then we have the IB, isolating the IB so that we will get IB is equals to VCC minus VBE over RB. Then we have the collector emitter loop. So on the other side of the diagram, we have this one, this portion here. So we have the VCC down to the RC to the resistor here, then the VCE. So this is the VCE. this portion here, the collector, the voltage across the collector and the emitter. Okay, so going down, then we will get an equation. So the loop will goes like this. Okay, so we will get the equation, and for collector emitter loop, making use of the presence of the beta. So since it is an amplifier, so we have a given beta here. So IC is equals to beta IB. So this is a standard formula for the fixed bias configuration. IC is equals to beta IB. So going along with the loop, so we have VCE going up, this one going up, going outside the positive polarity. We have VCE plus ICRC minus VCC is equals to 0. Isolating VCEs, and we will get VCE is equals to VCC minus ICRC. So if you already understand and know how to do a looping, okay, for the how to trace the current flow, so it will be easier for you to formulate this equation. So you don't need to memorize all these formulas. You have another is when we say VCE, so that is the voltage across the VC and the collector voltage and the emitter voltage. However, at this is a common emitter type of transistor, so our the emitter is being connected directly to the ground, and then so we will get VCE is equals to VC being VE set to 0, so that is just 0 there. Then we have also VBE, voltage across the base and the emitter, that is also be interpreted as VB minus VE. And since VE is equals to 0, so VBE is just equal to VB. Then we determine the following for the fixed bias configuration. So this is an example of a circuit pertaining a fixed bias configuration. So we have here an NPN type of transistor. Okay, so here we are asked to find IBQ and ICQ. Okay. Then we will find for VCEQ, VB and VC, and the VBC. So Q here is what, as we have discussed earlier, it is about the quiescent point wherein the transistor is in operating mode. Okay. So to get the IB, so our IB is this one. Okay. So this is the flow over IB. So we'll make use of the current flow. So here, to solve the IB, we have to do a looping here, VCC. Oops, wait. So we have VCC minus IBRB. Oops. Minus the VBE equals 0. So we have the value for VCC, we already have a value for RB, and we also have VBE. So what is VBE? So, ay, nakat naman di ay. Okay, so what is VBE? So VBE is known as the value, the standard value, the value known for silicon is 0.7 volts. Okay. Wherein it starts to operate. Okay. So we have, oops, wait. So VCC. So we isolate IB, the other side. Our equation goes like this: VCC minus VBE over RB. So that is just 12 volts minus 0.7 over our RB is 240 kilo ohms. 240 kilo ohms. So calculating, we will get, okay, so my storage is full. Okay, so answer will be 47.08 microamperes. Right. So we already have the value of the IB. Now we proceed in solving ICQ. So this will be the current here going down to the emitter. So, however, we can get IC by using the formula stated earlier. IC is equals to beta IB, right? Because we already have the value for beta, this one is already given, and then we also got the value for IB. Therefore, we could automatically substitute the values. So 50 times the value of IB is 47.08 microamperes. So we will get 2.35 milliamperes. That will be the value for our IC. And at this portion, we will solve for the VCEQ. Okay, the current, the voltage across the collector and the emitter. So this one here. Okay, we can solve this by doing a looping here. So from the VCC minus the voltage across the RC, which is we also identify as ICRC. Right. So we already have values for our IC, so we can solve this directly by 12 volts minus IC is 2.35 milliamperes times the RC, which is 2.2 kilo ohms. Oops, sorry. Pasensya na sa agi, guys. So, lisod kayong mouse. So, we will get the value. So, what do you get? It's correct. So, it's 6.83 volts. So, this will be our VCE. Now, we solve for the VB. So, it's just the voltage across the base. Okay. And VB can also be known as the VBE. So remember, we have here a common emitter type of configuration. So our VB will also be 0.7 volts, knowing that our emitter here is 0. Okay, so that is 0. Now, we solve for VC. And VC is just equal to VCE. Okay, or the VCEQ, just the same. Okay, and since our emitter also voltage emitter is just 0, so that would be 6.83 volts too. All right, now we solve for VBC. So our VBC is just the voltage across the base and the collector here, base and the collector, and we just have to subtract. So that is just VB minus VC. So VB is 0.7 volts minus 6.83 volts. So we will get a negative answer here. We have negative 6.13 volts. Okay, so the negative sign here is an indicator. It is revealing that the junction is reverse bias. This one here, this being reverse bias, as if you remember, as it should be for linear amplification. All right. So much for that. So now we proceed for the transistor saturation. The term saturation is applied to any system, okay, to any system where levels have reached their maximum values. For a transistor operating in the saturation region, the current is a maximum value for the particular design. So if you change design, and the corresponding saturation level may rise or drop. Of course, the highest saturation level is defined by the maximum collector current. So as you can see here in our graphical representation, so we have here the IC. Okay, so the if you want the highest saturation level, so you have to define the collector current. Okay, the maximum by the is being defined as the maximum collector current as provided by the specification sheet. So the looping for that would be here. So we have this RCE is equals to VCE over IC, or the IC RCE. Okay, so RCE is just equal to 0 ohms. Then our VCE is equal to 0 volts. IC, this is for saturation. Okay, and then IC is equal to IC sat. So our RCE is just equal to 0 ohms. Now, our IC sat is equals to VCC over RC. So remember that formula. It's just the IC sat is equals to VCC over RC. Next. So now, we need to determine the saturation level for the network. Okay, so we solve for the IC sat. So just using the formula IC sat apps. Wait, sorry. So IC sat, okay, saturation point. Okay, IC sat is equals to VCC over RC. Okay, so equal sign should be here. Okay, it's equals. So our VCC is 12 volts and our RC is 2.2 kilo ohms. It's this. So answer would be 5.45 milliamperes. So this will be the collector current saturation level.